Welcome to the second part of our tutorial, which focuses on the practical application of our Stepper module. My name is Volker Marks from Kendrion, and in this video I will show you how to quickly and easily configure the Stepper module in CODESYS using a small basic project. Before we start with CODESYS, here is a brief overview of the hardware used. We are using the FIO controller 111 as the head controller, our compact CODESYS controller with a multifunctional interface. There is also a separate tutorial for this controller. In addition, we are using our FIO Stepper module, which can control up to 3 axes. In this tutorial, we are using the first axis. Please remember to connect the power supply to the motor. We are using the English version of CODESYS 3.5 SP19 Patch 7. And one more note. The complete project shown in this tutorial, an application node, and the motion library can be found in our product finder, link below the video. When you open the project archive, all the necessary device descriptions and the library are automatically installed. This gives you a ready-to-run sample project that can serve as an ideal basis for your further work. And now let's get started. On to the practical part. We start CODESYS and select the downloaded archive via File Open Project and click on Extract. We decline any questions about updates. In the Library Manager, we find the library for the Stepper module, KESC_FSC. In the POU folder, we now see all the function blocks. We will take a closer look at these later. Before using these blocks, they and the associated axes must be declared. We switch to the folder GVL and find the global variable list with the declarations there. First, the axes. Each of the axes is of type AxisRef. To avoid confusion with other motion libraries, a namespace prefix is always added. Since we have 3 axes, this declaration exists for each axis. Then first, the function blocks that apply to all axes, control limits and read axis error. More on this later. This is followed by the instances of the blocks from the library, again for all 3 axes. Now these instances need to be called up. This is done in the PLCPRG block, which we find in the POU folder. Since we are passing pointers to the process image, we wait until the EtherCAT master is initialized and does not report any errors. Initialization only takes place at startup and is locked via the xinit flag. The slave address is transferred here for each axis, and since we only have 1 slave for all 3 axes, it is identical for all axes. Axis slot is the slot of the respective axis. The value here is therefore 1 for the first axis up to 3 for the third axis. Now the pointers to the process image must be transferred so that the blocks are also supplied with the module data. The addresses CW and SW have been entered in the respective process image. Here is the example for axis 1. CW1 is the first variable in the output process image, and SW1 is the first in the input process image. When initialization is complete, the instances of the motion blocks are called. First, the blocks for all axes, and the name of the axis is always transferred. Since these blocks apply to all axes, it does not matter which axis is used here. Then the axis-specific blocks. Here too, the respective axis is always passed. Axis 1, Axis 2, and Axis 3. That's all the program you need to put the axis into operation. Since this is easier and less complicated with a visualization, and the motion library provides a visualization for each block, we will now switch to the visualization of the first axis. Each visualization has the corresponding block from the global variables as a reference. For example, MC_power has the reference to power_01. Only the visualization of the axis VZ axis has the axis itself as a reference because there is no block there. Let's now move on to the configuration of the stepper motor. In the startup parameters of the respective axis, here axis 1, you set the specific parameters of the connected motor. The first 5 entries are for the current. Maximum current refers to the maximum phase current, which can be found in the specifications. This is 3 amps. We set the current for the ramps and movements, deceleration, acceleration, and running current, with regard to noise and power consumption. No more than necessary, but high enough for the maximum load in the application. Holding current, i.e., the current that flows when the motor is stationary, depends on the application and must be activated for the respective axis via bit 3 of the motor drive submode select object. We set this current to 250 mA for our axis and activate it via bit 3, which corresponds to an 8. Then pole pair count. This is the number of pole pairs. The module supports the most common stepper motor type, which is the bipolar two-phase stepper motor. The value for pole pair count cannot be found directly in some documentation, but can be determined via the step angle. Here, this is 1.8 degrees. Pole pair count is 360 degrees, divided by the step angle times 4. 4 is the number of switching states of such a stepper motor. In our case, this results in a value of 50 for the pole pair count. Then there is the value for encoder increments. Of course, the module does not have a real encoder, but this object is used for compatibility reasons to set the microstepping of the motor. The table shows the possible values from full step, i.e., 200 steps per revolution, up to 16 times the resolution, which corresponds to 3,200 steps per revolution. Here you can see how halving the encoder increments doubles the maximum speed. Of course, this table only applies to this example and changes with changes to the pole pair count, gear factors, or feed constants. So select the value that will allow you to still achieve the maximum desired speed in your application. Have you set all the parameters? Great, then it's time to get things spinning. We log in and start the program. The FIO controller 111 still requires a username and password, both of which are administrator here. We start the program and wait until the EtherCAT tree turns green. The central module is MC Power. We set the 3 inputs, enable, regulator on, and drive start to true. The status turns green, which means that the drive is powered and ready to run. We test this immediately with the jog block and move the axis in both directions. In Axis Visual, we can see how the axis is moving, but let's take a closer look at the blocks. MC Power. This block activates the axes by starting up the state machine and making them ready to move. To do this, all 3 inputs are set to true, and you can see in the output status whether the axis can now be moved. Then there is the red status block. This provides you with an overview of almost all states of the axis. First, the axis errors and warnings with the axis error code, then the errors that were detected in a function block, the position of the axis, its current speed, and the status. In addition, the error messages are also displayed in plain text. Let's generate an error. We deactivate the axis in the power block and then try a jog movement again. An error appears in the function blocks in the read status block, and we also see the error in plain text. We acknowledge the error with the reset block, which takes us to the next block. We switch the axis back to ready in the power block, and the axis can be moved again. The MC jog block, which we have already used, is used to move the axis in manual mode. The speed and the 2 ramps are transferred here. What range can these values be in? The control limits block is used for this purpose. Here, the current values for minimum and maximum speed and acceleration can be calculated and displayed. Please note that these are only calculated once the axis has been activated with the power block. The values on the left are in user units per second, and on the right in revolutions per minute for the speeds, and in revolutions per second squared for the accelerations. So, with a value of 64,440 for the speed, the maximum speed is 1208 revolutions per minute. Let's now move on to the 3 central modules for axis movement. Move relative moves the axis to the specified position, move absolute moves it to the specified position, and move profile velocity is used to operate the axis in speed mode. As with MC jog, there are also parameters for the speed and the 2 ramps. To make it particularly easy for our customers, there are 2 options for entering speed and acceleration. Using the XEasy Values switch, you can also set these in the very clear units of revolutions per minute for speed and milliseconds for ramp length. We activate this flag in Move Absolute and move to position 5000. The speed should be 60 revolutions per minute and the ramp length 1 second. MC Home is used to perform a reference run. Pause is the actual position after the reference run, and method is the homing method. Please refer to the stepper manual for this information. We use method 37, which corresponds to referencing at the current position. The actual position should be set to 1000. If we use a 0 here, the axis can be reset to the 0 position. Then there are the two blocks that can be used to stop or cancel a movement. MC Halt interrupts the current movement with the current ramp and waits for the execute to be removed before continuing the movement. However, this only happens if the stop bit is not set. Otherwise, the axis stops the movement it has started without resuming the movement. We delete the stop bit and start a movement to absolute 50,000. Then we trigger a stop. After removing execute, the axis starts again and now completes its current movement. MC Stop also interrupts the movement and stops the axis, but here a brake ramp can be transferred in order to be able to brake more quickly in dangerous situations. The two SDO blocks are used to write and read a register, and you will find a detailed description of this in the manual. Then the last block, read axis error. This displays the last 8 axis errors, which can be very helpful for diagnostics. If, for example, we interrupt the motor supply, the axis error under voltage occurs. We restore the connection and acknowledge the error with MC Reset. Then we activate the positive limit switch. Again, an axis error is generated. Now we can read out these last 2 errors with read axis error. We have now reached the end of this tutorial, which is designed to give you an easy introduction to programming our 3-axis stepper module. Further information and assistance can be found below this video in the form of linked documentation, examples, and instructions. Thank you for your interest and good luck with your motion projects.